Here's a rule that you may find helpful when you're trying to figure out what to let u be and what your dv should be. Most integrands are built from functions of five types: logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. The LIATE rule suggests choosing u in that order. Make your u logarithmic first if you have that in your integral. Then, if you don't, try using inverse trigonometric as your u. If you don't have that, try an algebraic statement, which is just basic variables with before basic operations. And very often that'll work if you try the functions in this order. So now we'll do a few advanced examples of integration by parts. And again, this stuff, A, is not simple, and B, you have to be willing to persevere and realize you're not always going to guess things right on the first try, and you have to go back and figure it out. So in this one, if I'm using that LIATE, if I'm keeping that in the back of my mind, inverse trigonometric is showing up here. I've got the inverse tangent. So most likely my u is going to be inverse tangent. And if you haven't seen that in a while, the derivative you should be able to look up. It's a fraction. It's 1 over 1 plus x squared dx. My dv is supposed to be everything else, which the only thing left is a dx. And certainly that is very easy to take the integral of. So I get v equals x. So far things seem to be progressing well. I'm going to go ahead and write my integration by parts formula. So u times v minus the integral of v times du. Now, once I get to this point, again, this all hinges on me being able to evaluate this new integral that I have created. And in this case, this is not a simple integration. You have an x times a fraction. Now, I can multiply that x into the numerator. I'm going to step off to the side here for a minute and do some thinking. And that would give me the integral of x over 1 plus x squared dx. Now, you did work with fractions like this when we were learning u substitution. So I'm going to go ahead and give u sub a try, where I let my denominator be my u. I take the derivative of u, which will be 2x dx, and I move my constant over to the left side, giving me x dx. Now notice, conveniently, I do have an x dx in my integral. And then the rest of it, I have the 1 over u. So I can now write this as a u integral. It's going to be 1 over u. U is the 1 plus x squared. The x dx gets replaced by a half du. The integral of 1 over u is the natural log of u. And the final step here would be to make sure I substitute back my u. And my u, because it's 1 plus x squared, whatever number I put in here, this will become positive, so I can drop the absolute value bars and just write 1 plus x squared plus c. I can now take this expression and bring it back over to my original problem. And that does give me my final answer. So yes, you're going to have to be able to use u substitution within an integration by parts problem, potentially. Now we'll look at example 8. In example 8, I've got two functions here. I kind of see a natural split. And again, if we're keeping this rule in mind, I don't have any logarithmic statements here. I don't have any inverse trig. I do have an algebraic statement. X squared is an example of an algebraic function. It's just a function of x. Technically, it's x times x, but again, as long as it's basic for operations, that's algebraic. I'm going to try using U for integration by parts and do all the rest of the setup. And as you can see, so far, this is going pretty well. My setup seems to work. I'm going to now substitute it into the integration by parts formula and see what new integral I get. So after my substitution, this is what I'm looking at. I'm going to go ahead and take my constant out of that new integral so I can just see what I'm dealing with. Algebraic part in front. And this again has got a product in it. And again, when we're working with products and integrals generally, we want to try and do integration by parts. So again, this is going to be one of those situations where I'm going to want to take this integral off to the side and do some work on it. I'm going to choose U to be the algebraic portion. So that x, so du is dx, which is nice and simple. My dv, I'm going to let be the e to the x dx. And when I integrate that, I'm going to get that v equals e to the x. So this does seem to be working out okay. Now I'm going to use the integration by parts formula just on this. Now I step to check my new integral, and phew, it is something that is easy to deal with. So I've got one more step in figuring out this integral. The integral of e to the x is still e to the x. So now that I've been able to evaluate this integral, I can now take what it's equal to back over to my original. And when I have brought it back over, notice I just leave the constant c at the end. There's no need to put it inside this set of brackets here. It doesn't need to get multiplied by 2. A constant is just a number, so that's not necessary. And I'm just using the square brackets to be careful here because, again, I had already pulled out my constant. So the last thing I would do is just distribute that constant to the inside. And that would be my final answer. Now, this last example is actually showing us a pattern that happens very often. You can see how we had this integral and it had a product and it had an x squared. And when we did integration by parts the first time, it lowered the exponent on the algebraic term by 1, and then we kind of had to do it again to be able to get to our final answer. This is known as reduction rules of integrals. This equation is related to the problem we just did. If you have the integral of x to a power of n times e to the x dx, you can just substitute into this formula and it will automatically take you through this process of reducing this exponent n until you get to a place where you're able to evaluate your integral. This works for all integers as long as n is bigger than 0. This is called a reduction formula. There are a lot of different expressions that can benefit from this reduction process. So let's see how this works. I'm going to use this reduction formula to evaluate this integral. Now, the first thing I want to observe is that my n value is 3, and since 3 is greater than 0, my reduction formula applies. My reduction formula says that when I want to evaluate x cubed e to the x times e to the x dx, it will always take this form. It's going to be x cubed e to the x minus 3 times the integral of x to the 3 minus 1, or 2 power, e to the x dx. So again, I've reduced the exponent on the x from a cubed to a squared. I can use the reduction formula to evaluate the new integral. So again, I'm going to go off to the side here. I'm just going to take the integral of x squared e to the x dx. I'm going to use the formula. Which gets me to here. now I have x to the first power. And actually, if I do one more reduction, I'm going to be able to get that x out of there entirely. But this is where you can start to get confused because you're taking an integral, then a subintegral, then a subintegral. So at this point, I'm going to take this, where I've gotten to, put it back over here so I don't lose sight of where I am in the overall problem. In place of this integral after the 3, I'm going to replace it with the red underlined portion. Now I'm going to step out to the side again to work on this integral, which is the x times e to the x. If I apply the reduction formula with x, with n equal to 1, I get x e to the x minus the integral. When I put in x to the 1 minus 1, I get 0 e to the x dx. And that's good news because anything to the 0 power is just 1, leaving me with the integral of e to the x dx, which is finally a nice integral that I can evaluate. So I will get x e to the x minus e to the x. And I will need to put a constant back on, but you can kind of wait on that and just put it on your final answer. So I'm going to take this expression back over to the original problem. I'm going to push this back a little bit because I need some space. I've got the x cubed e to the x, then I've got a minus 3 times x squared e to the x minus 2 times the red underlined portion, which is equivalent to this integral. So I've got 2x e to the x minus e to the x. Close all my parentheses with a plus c. And you can clean this one up a little bit by using some distributive property. And there is my final answer. And you see in the terms, I've got these nice descending powers of x. So a reduction formula may need to be applied repeatedly. And what it will do is eventually work the variable out of there so that you get an integral you can evaluate.